This week in lab, we'll finally get to do experiment 18. I know you've been anticipating this since the final exam. We finally get to do it. Extra bonus, we'll have a quiz this week. So, because we missed a week, we don't want to give you one less quiz. So, we'll have a quiz this week. It'll cover experiment 18 and information that I go over for experiment 16 as well. Next week, we'll be doing experiment 17, part 1, so we'll just do the first half of it. So, but do have your pre-lab for the entire experiment. It's a 2-week experiment. Next week, have your pre-lab for all of experiment 17 ready to go. Okay. And then in amongst doing the first part of experiment 17, we're going to teach you how to process NMR data, and we'll use your experiment 18 spectrum. So this is the one piece of data you probably won't have for experiment 18 until next week. Then in 2 weeks, right away, we start with due dates. Things are moving right along. Experiment 16 and experiment 18 are due 2 weeks from this week. Reminder, open lab times, same as last semester, Monday, Wednesday, Friday, 9:30 a.m. to 3:30 p.m. Subject to change depending on things going on in the department, seminars, so on and so forth. But these will be the general open lab times, just like last semester. So I'm going to start with the syllabus here, kind of cover the high points. I'll let your lab professor go into more detail with the syllabus. The overhead doesn't want to really cooperate and show things very well here. So your lab manual, your yellow lab manual you had from last semester, same text. So see, we gave you a discount. You don't have to buy a second lab manual. You got 2 for the price of 1. You want to have your lab manual. You want to have a new lab notebook, unless you got a new one last semester and use less than 20 pages. Make sure, just like last semester, bring a pen with you, have a Sharpie with you, all those kind of things. Top part of the syllabus gives you all of the lab times and who's teaching when. I have Tuesday and Thursday morning. Dr. Sanford has Tuesday afternoon. Dr. Gilmore is with me Thursday morning in 3129. And then Dr. Johnson, who was on sabbatical last semester, now will be teaching in the lab again. We'll have Thursday afternoon. So there's a lot of information about the semester here. I'll have you read over that. But one big thing here, on Monday, February 24th, we will all gather together, just like we did for the final exam. We're going to get together for the midterm exam. So because some of you will be taking the course for 1 credit and be leaving right after the midterm exam, that is the one time we can get you all together to take 1 exam together, okay? So Monday, February 24th at 4 o'clock in this room, the midterm exam will be given, and it'll be an hour exam, unlike the final exam that was a 2-hour exam, okay? And then more specifics there, I'll let your lab prof go into. Here is our schedule, our now revised schedule. So we dropped a week of lab. The week we dropped is experiment 20, used to be a 3-week experiment. It's going to become a 2-week experiment. And when we get to experiment 20, we'll explain how that can be possible. Okay. So it's not that we're going to make you do like 2 parts in 1 week or something like that. We've just eliminated one of the pieces. So first part of the semester, here is the schedule, pretty similar type of schedule to what you had first semester. We give a quiz every week, except for the week of winter break, when Tuesday labs won't meet, obviously, because winter break. So Thursday labs won't meet either. We'll just have open lab on that day, okay? But otherwise, the other 5 weeks that we are meeting to do an experiment, we will have a quiz. And then the last week of lab, on the 25th and 27th, for 1 credit people, you will be checking out. And then those that are taking the lab for 2 credits, we will be working on starting our independent project. Okay? But again, remember, Monday, February 24th, everybody in here, 4 o'clock for the exam. Okay? The 3rd page has the grading scale on it, so you can compare lab notebooks. We've got an hour exam that's only worth 50 points because it's half of what the final exam was and half the semester. We've got 5 quizzes, and then you've got lab, technique, and safety. That's 25 points instead of 50 points because, again, it's half the semester. So this is for the first credit. There's 350 points possible. For the second credit, then you add another 250 points in what you will do for the independent project. Okay. And then there's more details about the lab itself. Because we are expecting that you have participated in first semester lab, you are aware of safety rules, aware of how things should be handled, chemicals and so forth should be handled in lab. You are aware of using your lab notebook, general lab rules, and then the information for Americans with Disabilities Act, and then on the last page is also information about academic integrity and course evaluation. So in lab itself this week, we'll probably discuss that more. Are there any questions about the syllabus? Okay, and this syllabus is the syllabus I have posted on Moodle. This is the syllabus that I also emailed to you. Okay, so you should, in many ways, have a copy of the syllabus. So now we're going to jump into experiment 18. And so, experiment 18, sorry, it's kind of dim here. This is also from the front page of experiment 18 in your lab manual, if it helps to look at that as well. Experiment 18 is a lot like experiment 6. You've got an unknown that you're going to determine what functional group is present, and then after you figure out what functional group is present, you're going to then figure out what unknown you have. It's just we've made it a little more complex because now we're into second semester and you've learned more functional groups, and we're going to learn more tools to investigate what functional group you have, okay? And so there's 2 categories of the possible functional groups you could have in your unknown. You either have something containing oxygen, so an alcohol, phenol, ether, aldehyde, ketone, carboxylic acid, or an ester are the oxygen-containing functional groups. And the nitrogen-containing functional groups are the amine, amide, nitrile, or a nitro compound, or nitrogen and oxygen. And so you're going to have one of these functional groups present, and in some cases the nitrogen groups actually have a couple present. So you're worrying about identifying what of these types you have in your unknown. There's also some secondary functional groups that could be present as well. And so on the first page of the experiment, it lists what other functional groups could be present. And so you could have a double bond, you could have a triple bond, you could have an aromatic ring, or you could have a halogen. And so you need to keep in mind these other secondary functional groups. So you could have one of those and one of these, okay? Or multiple of these. So our double and triple bond, how would we test to figure out if we have that or not? Bromine and the permanganate test, right? Okay, so everybody should be doing a bromine test and a permanganate test on their unknown so that you can test for these guys. How would you figure this guy out? Do we have a test yet for an arrow group, really? Not so much, okay? But we've got other things we're going to use. We've got, you're going to collect an IR spectrum, you're going to collect a GC mass spec, and you're going to collect a proton NMR. So those are all things that can help give you information about whether or not you have an arrow group in your compound. So the spectroscopic data is going to help you out with this guy, okay? Halogen, how do we test for that?
Flame test.
Our Beilstein flame test, right? So everybody, again, should be doing this test. And then, what else could we use to figure out which halogen we have? mass spec, right? And so you guys, I'm not really going to go into too much detail about this guy because you covered it in pretty heavy detail during lecture last semester. But you can use GC mass spec to figure out the isotopes and the splitting patterns of the isotopes, what halogen you have, okay? So if you get a positive flame test, that's telling you, use your GC mass spec and confirm that it looks like it has a halogen, and then figure out which halogen is present from that GC mass spec, okay? So I am going to go through this flow chart that is in your lab manual. It's on page 18-6, figure 18.1. We're going to talk about, so our flow chart got a little bit more complex than it was for experiment 6. So we need to talk about, we've got tests in here you've seen before, but we also have new things in here that we need to talk about for you to look at as well, okay? And the other thing we're going to talk about is just kind of give you general guidelines for all the things that you're going to need to collect about your unknown. So we've already talked about a few of them. We're going to definitely need a Beilstein flame test. When I get to talking about the chemical tests, I'm going to lump bromine and permanganate in with the chemical tests. Just remember that you do need to do those tests as well. As far as spectroscopic data, you're going to collect an IR. You're going to submit a GC mass spec sample. We'll talk about that here in a little bit. And you're going to submit a sample to look at proton NMR of your compound. Okay, so those are the three things that are going to be collected of your compound. You need your physical properties data. So for experiment 6, you all had liquids. This time you're going to potentially have a liquid or a solid, okay? So you either need to collect a boiling point or a melting point. Then we're going to do solubility tests. And each of the different functional groups has information in experiment 18 about different solubility tests that you can consider for those functional groups. Do remember the table from experiment 6, and remember how to read the table from experiment 6, and that is on page 6-8 is that solubility table. Remember with the table that if you get a certain pattern in the table and then all of a sudden it tells you not to do the rest of the tests, don't do the rest of the tests, okay? So remember to follow the solubility table in order and test those solvents in order, and if all of a sudden you get this guy, it means don't do the test, okay? In addition to that solubility table, a lot of the functional groups are going to have you test for solubility in sodium bicarbonate. Okay, so that will be available. Sodium bicarbonate solution will be available for you to use. Then we have our sodium fusion test that I'm going to talk about here in a minute. And we have the rest of our chemical tests. So with this flow chart, it basically starting with that sodium fusion test. We need to decide, so we have these other things that we can be doing, but we're going to, from the get-go in lab this week after we've done the quiz and introduction and got everybody into drawers and checked in, we need to start right away getting everybody doing the sodium fusion test so that everybody has a chance to get through it in the entire lab period, because it takes about 15 minutes or so per person to go through it. This sodium fusion test is going to tell you either nitrogen is present, and so you're going to go on and do start with page 18-8 in your lab manual looking at solubility and chemical tests for nitrogen, or nitrogen is not present, and then you're going to go through this flow chart, okay? So if you find out from your sodium fusion test you have nitrogen, you're not going to use this flow chart, all right? If you don't have nitrogen, then you're going to start going through the flow chart. So what is happening with that sodium fusion test? What you are basically doing is fusing the sodium to the element that you're looking for. So we're going to start with a sodium in parafilm wafer. So we're not just sodium, as you remember from Gen Chem, it's very flammable. We're not just going to pull sodium out into the organic lab and try and not start a fire, okay? So the sodium is in a parafilm wafer. You're going to stick that into a test tube. You're going to melt it. Then you're going to melt the parafilm. Then you're going to add your compound on top of that. And what you're trying to do is fuse the elements that you're looking for specifically to that sodium if it is indeed in your compound, okay? And the sodium fusion test is described on page 6-5, the instructions at least in your lab manual. And the only part that we're going to do is the part testing for nitrogen. So there's more tests that you can do to figure out what halogen you have. Those are sometimes reliable and sometimes not so reliable, okay? So we're not going to test for the halogens. You're going to do the Beilstein flame test. If it's positive, use your GC mass spec data to figure out what halogen you have, okay? So we're only going to be looking for nitrogen. And what happens is you basically have an organonitrogen compound, so an organic compound that contains nitrogen, and we're going to heat it very hot with sodium. And what we're going to form is sodium cyanide. So this nitrogen comes from your compound. The sodium comes from the actual sodium wafer, and we've got plenty of carbon because we're going to char the heck out of things in there as well, okay? And so then we have this solution that contains the sodium cyanide. We'll end up quenching the sodium, mixing everything in water, filter out all the charcoal, and we're going to take this guy and make it saturated, have a solution saturated with bicarbonate, and then this is going to react with paranitrobenzaldehyde, and that is going to give this deep purple color. So if we take this, you end up forming this species, I would say, and it's a deep purple color. It's like, if you think of color here. If you think of like eggplant, like that deep of purple, almost looks like black instead of purple. Like you kind of may have to tilt the test tube on the side to actually see the purple, okay? So it's a very, very deep purple color. And the reason why I'm emphasizing that is some compounds give kind of a false positive test for nitrogen, and if you get a light purple color, that is most likely not a positive test for nitrogen, okay? It really needs to be an intense purple color, okay? And so make sure you read over the instructions in experiment 6 for doing the sodium fusion test, and we're gonna have TAs basically stationed right at the flame hood to help you out with the sodium fusion test, okay? But in the end, what you're looking for is this deep purple color of the cyanide reacting with the paranitrobenzaldehyde, then you have a nitrogen. If you don't have that color, then you don't have a nitrogen. And so then we're going to work through this flow chart. And so what we start with the flow chart is if we don't have nitrogen, we're going to start over here on the left-hand side. First thing we're going to do is the 2,4 Dmp test. Okay, so same test as you used in experiment 6, and that test in experiment 6 we were just looking for ketones, but it actually will give you a positive test for a ketone or an aldehyde. Okay, so if you get a positive test at this point, you have an aldehyde or a ketone, but you don't know yet what you have. Then we're going to use the chromic acid test. This test you'll go over in a little more detail when you get to reactions with aldehydes and ketones in lecture. But basically what we've got our, first we'll look at it with the aldehyde, it reacting with chromic acid. Then it forms, then it's going to form a carboxylic acid and then chromium sulfate. And so this reaction with an aldehyde takes less than a minute. It really doesn't take very much time at all. You get your acid, and this is kind of like an orange, almost red. It's more orange than red solution, but it's colored solution. Your aldehyde probably isn't very colored. But what you're forming when it reacts is the chromium species. So this chromium 3 species is like a blue-green color, and it may be even a blue-green precipitate. And so that's what you're looking for. If you get a quick reaction, you have an aldehyde. If you don't get a quick reaction, then you have a ketone. And this guy usually for a ketone, if it reacts at all, usually is greater than 2 minutes, okay? And so then you may, like after 2 minutes, you may see this blue-green precipitate. So you may see either no reaction, or you may start to see this blue-green precipitate forming, okay? If you look at McMurray, it'll tell you chromic acid won't even react with the ketones. So it kind of just depends on the ketone, okay? But you're testing, was it a really fast reaction? Yes, it reacted with an aldehyde. Was it a slow reaction or no reaction? Then it was a ketone that you had, okay? And if you're a little bit confused about it, because in this orange-red, sometimes it's hard to see the growing end of that blue-green, make sure you check with your lab prop, okay? Same with the sodium fusion test results. Make sure that you verify those with your lab prop as well. Now, one thing with the chromic acid is you do not want to get chromium in general on you, and you do not want to get chromic acid on you, okay? So make sure, be really careful with it. Make sure you're wearing gloves with all of these unknowns. They're more complicated, so a little more toxic than what we were using last time. I would wear gloves throughout the experiment, but be especially careful with the chromic acid test, okay? It's going to be in the reagent hood, often a beaker by itself, isolated, because it is so reactive with so many things, and be really careful when you handle it, all right? So if you get a positive Dmp test, then you're going to do the chromic acid test, and then see what you get. If you get a negative Dmp test, then you're not going to do the chromic acid test because you didn't have an aldehyde or a ketone. We're going to go down this side of the flowchart. And so then we're going to start with the ferric chloride test. And this is a test for whether or not you have a phenol or not, okay? And so ferric chloride will complex with phenols, so there's not really a reaction to show it's a complexation. And that phenol can be kind of a red. It's not really very descriptive because it's like, well, it could be red or green or blue or purple, so kind of almost any color under the sun. But if the ferric chloride itself is not highly colored like that, so if you get any of these red or blue or green or purple, then you probably do have a phenol, okay? If you don't have a phenol, if you get a negative test, then you're going to go on and do the Ceric ammonium nitrate test. And the reason that we do it in this order is otherwise it'd be hard to figure out if you have a phenol or not, because Ceric ammonium nitrate is going to test positive for alcohols and phenols, versus here we can do a test, figure out if you have a phenol or not. If it's not a phenol but possibly an alcohol, then do the Ceric ammonium nitrate. If it's an alcohol, then you're done there and you're not confused between whether it's just a regular old alcohol or a phenol. So Ceric ammonium nitrate test, same test as you did for experiment 6. If we don't have an alcohol, then we're going to do the hydroxamate test for esters. And so again, this is another test you'll see this reaction in experiment or in future chapters in lecture when you get to where you're talking about the esters. And so if we have an ester, we're going to, you actually start with the salt of this, but what we want to form is hydroxylamine. So we start with hydroxylamine hydrochloride, and we then form the hydroxylamine actually in solution. And your lab manual says that we use sodium hydroxide, although in the instructions we actually use potassium hydroxide. So the picture shows sodium hydroxide, but I'm going to say or potassium hydroxide because that's actually what we truly use in ethanol. And then you're going to heat it. And you reflux it for a little bit of time in the test tube. So you're going to, in a hot water bath, reflux it. And then what you form is this species if you do have an ester. And so this is called hydroxamic acid. So instead of just carboxylic acid, we have the amine part of it. So that's why it becomes hydroxamic acid. And then you also form an alcohol. Now, in order to visualize that we have actually formed this, then you're going to do add a little ferric chloride to it, and the ferric chloride, again, you've got a complexation reaction. It's going to then make this colored so you can actually see it. Okay. And so that's what the ferric chloride at the end is. And so you're looking for the formation of that color to tell it whether or not you have an ester or not for that reaction. Then, if you still don't get a positive test, working our way down here, then we're going to decide if we have a carboxylic acid or what will test negative for everything. In experiment 6, that was the alkane. In experiment 18, it's the lucky ether. You will just do a regular solubility test in NaOH. If you get to this point in the table and you get a positive test in NaOH, then you have a carboxylic acid. Negative test, then you have an ether. Okay, and so if you got negative for everything, negative sodium fusion, and negative for every test in this flow chart, then the functional group that you most likely have is an ether. Okay, and you'll be able to confirm that with your IR spectra, your NMR spectra, with your GC mass spec, being able to look at those and confirm that it is definitely an ether, but there isn't a characterization test for just the ethers to say yes that you do have it. Okay. Now with the nitrogen-containing compounds, there's a couple things you're going to do. You want to read through the pages on the nitrogen-containing compounds because there's information about what you need to look for in your IR. Also information about solubility, but there's two, they label them as two chemical tests. One is just trying to dissolve your unknown in water. And if when you do that, you check the pH and you get basic pH, then that's the sign of an amine. So if you get an amine to dissolve in water, it usually will give you a basic pH. Okay. Both of these tests have to do with amines. Then another chemical test that you can do is a copper sulfate test. So basically, you're going to add copper sulfate to a sample of your amine. You get a complexation reaction with this test. And what color usually do you see from copper sulfate? Kind of blue turquoise color. You get a blue turquoise precipitate if you have an amine and it reacts with the copper sulfate test. Okay. So you want to test both of these if you do have a nitrogen-containing compound, because you are trying to figure out if you have an amine or not. Otherwise, if these don't end up working out for you, there's other information in the nitrogen portion to tell you what to look for in the IR and what other solubility information you need to look for to kind of figure out what it is of the nitrogen groups, okay? So for lab this week, basically we need to get through, I guess I should have left that up there, oh well. You need to get through everything, all of the possible tests. So we're going to need sodium fusion, Bilstein flame test, if you have a liquid, you want to collect the boiling point. You want to prepare your GCMS sample. And to do that, if you have a nice clean sample, you can take, if you have a liquid, you can take your GC vial, so you'll get a new GC vial, and put like barely a drop in the GC vial, and then fill the neck with pentane, or sorry, with dichloromethane. And so there's instructions in your lab manual. If you have a solid, use about 5 milligrams or so of the solid, not very much at all, and you're actually going to weigh it out. It's really important that you don't have too much in there. Fill that up with dichloromethane, and then same as when you prepared your GC samples, sample blocks, put it in, fill out your information on the sheet. We need your NMR sample, and so, whoops. We'll show you in lab how to prepare that, but again, there's another sample block. You put it in and then fill out your information, and we'll run these, and then on the notes for next week, this is the part where you'll actually process that sample next week, but we do need this in lab this week. We need the chemical tests done, and we need the solubility tests done. So the two things we've got not listed here are, it is possible you could collect your IR spectrum in open lab, and you could, if you had a solid, collect the melting point in open lab, okay? But the rest of this we need to get taken care of in lab this week. For the experiment, you're also going to want a literature spectrum. So for the report, you're going to want a literature spectrum for your IR, you're going to want a literature spectrum for your GCMS, and you're going to want a literature spectrum for the NMR, okay? On the page, I believe it's page 1616 of your lab manual, there's a bunch of resources listed for you, okay? So Aldrich Spectral Viewer is in the Duck Lab or any campus clone computer lab. SDBS you can get to by Googling SDBS, or the NIST webbook website you can use for your literature data, or if you want to go through the paper copies in 3123, you can use those, okay? But you need literature spectra for each of these, okay? And then you've got your report form for experiment 18 that's similar to experiment 6, except for you're going to collect more data for it. So make sure you look that over, so that if you have questions about it, you can talk to your lab prof this week about that, okay? So with this report, you're going to have your report form for experiment 18, all of your experimental spectra, all of your literature spectra, and the conclusion that you will write for this experiment, all right? So just don't forget that now, instead of just IR, we have IR, GCMS, and NMR. You're going to need all that literature data. GCMS will get you your experimental back to you after we've run it. So we'll let you know when that is available, just like we did with the GCs when we collected the data and then got it back to you. GCMS will have to hand that back to you. IR you're collecting on your own, and we talked about NMR. Couple things to remember about IR. Remember, you want a neat or a liquid or even for some solids, unusual mole is a possibility. So what they do is they take the solid and they mix it up with mineral oil and make it a paste and then collect the IR spectrum of that. You can use that as a literature IR spectrum, but what you need to do then is in experiment 5, let me recall, page 5-16 in experiment 5 has the IR spectrum of mineral oil. You need to look at that if you get a literature spectrum that's unusual mole. You need to look at that IR of mineral oil because you basically need to cancel the mineral oil out of your spectrum so you know what is left of your spectrum, okay? So just be careful with the IRs that you are getting one that's going to work for you. So vapor phase or gas phase isn't going to work. Even a lot of times if it says melt, a lot of times that's may not be so helpful, so possibly look for another source for that one too. With the NMR, we're going to collect all our samples using deuterated chloroform. So you'd like to find an NMR spectrum that was collected in deuterated chloroform too. So you don't have to worry about everything being shifted, okay? So a couple things to look out for IR and NMR with those literature data, okay? Okay, now we're going to kind of switch over here into experiment 16. So experiment 16 we're not actually going to do experiment 16 there's no in-lab part. There's a lot of information in experiment 16 that's going to be really helpful for analyzing NMR. And then the last 4 pages of experiment 16 and 1617 through 1621 are worksheets that you're going to hand in, okay? So you're not going to do anything in lab with it, but they're worksheets between what is covered in lecture and what is covered in lab that you're going to go over, okay, and figure out. So I'm going to go through an example problem using some of the tables, and then we'll talk about other parts of what's in experiment 16. So we've got this example problem here. And one thing with experiment 16, part of what you're going to look up are actual values for chemical shifts. Use Aldrich Spectral Viewer for those actual values. So you do have to go to the Duck Lab or another campus clone computer lab to use Aldrich Spectral Viewer for that, for the actual values. So in experiment 6, there's a lot of these type of tables that we can use to calculate chemical shifts, okay? So we're going to go through this problem here and calculate the chemical shifts for this particular problem. So when we're looking, we're going to start with the methyl and methylene protons here on the bottom. And we'll use this table here. So we're going to start with our methylene here. You always start with 0.23, and then you're looking at what is on either side of the group that you're looking at. So this methylene, we've got O and then arrow group, or we've got this methyl group. And so you want to look in your table here to figure out what is going to correspond to each group. So first of all, one side we've got the O arrow group, so we're going to add 2.94 to that. And then on the other side, we've got this methyl group, And so we're going to add 0.68 to it. And so what we get is 3.85 is our calculated chemical shift. Okay? We're going to do the same thing for our CH3 group, and again we're starting with 0.23. We've got our arrow group on one side, so again, we've got our CH2 arrow group on one side, and so you got to kind of use this table and see if there's really anything that corresponds to that in the table. And we don't have anything that says CH2 and then O arrow group. And so what we're going to use instead is just that we've got that CH2 on one side, so we use the 0.58. On the other side, we just have a proton, so we're going to add 0.34. And so then this guy is 1.15. It's calculated chemical shift. Then we have to look at the aromatic protons, and so we have to change our table. We can't use the methyl and methylene table. We've got to use one that looks at aromatic protons. And so with that one, we're starting out with our saying that we're going to use 7.27 as our starting point. And then we're going to add information for what is ortho, meta, or para from the compound that we're, or the proton that we're looking at. Now, another proton is worth a 0 as far as chemical shift, okay? And so starting with HA, if we look at what is ortho to HA, on one side we have HB, another proton, so that's 0. Or we have the cyano group, and so we're going to add from way down here 0.27 due to that cyano group. Then we want to look at meta. So meta to HA, we have itself, so another proton, that's 0. Or we have this ether group down on the bottom, and you want to make sure that you, when you're looking at these oxygen-containing groups, you're looking at the right one. So we want to, first of all, we're looking now in the meta column, and we want to make sure that we're looking at something for an O alkyl group. So we're going to look at negative 0.09 for that value. Then if we look at HA para to it, we just have another proton, so that's going to be 0. And so its calculated chemical shift is then going to be 7.45. For HB, we start with 7.27. And for HB, we have another proton ortho, or we have the ether group is ortho, and so we're back in the ortho position, but looking at our OR, so we take minus 0.43 for that value. Then HB, meta to HB, we have either the cyano group or we have itself. And so for the cyano group meta, we're going to look down here, we're going to add 0.11. And then para to HB, we have another proton, which is 0. And so the calculated chemical shift is 6.95. Okay, so now I'm going to look at like the actual spectrum for this compound and see how close we came. So here's the actual spectrum, and one thing I want you to notice is how I've labeled the peaks on the spectrum compared to the structure. So you want to always draw the structure and then label all the protons in the structure with a letter, a unique letter to that type of proton, and then label the peaks above the peaks with the letter for what protons it corresponds to, okay? And so our HA was more shifted than our HB, so HA's here, HB's here, so we've got about 7.55, 6.92, so we're kind of close to what we calculated. Our C's, we came up with a calculation of 3.85, and here we're about right at 4.06 or so, so that's pretty close. And then our D, we came up with a calculation of 1.15, and actually it's about 1.44, so it's a little bit off, but pretty close. So this is a way, in using the calculations, you can then figure out assignments in a spectrum if you don't know what they are. So that's a big part of why you would calculate things, is if you don't know where they are in a spectrum, you can help figure them out, okay? So that's part of experiment 16, is just calculating chemical shifts. What else you're going to look at in experiment 16 is also different types of coupling constants. So aromatic compounds with substituents, or sorry, with other protons have coupling constants in their spectrum. So if you've got orthoproton, we talked about, we didn't take that into account in chemical shift, but we do in looking at the coupling constant. And so an ortho set of protons are going to have a 6 to 10 hertz coupling constant. So that's fairly decent size. You'll see that in your NMR spectrum. Meta is 1 to 4, so depending on how strong, if it's closer to the 4, you'll probably see it, but maybe not so much if it's the 1. And then para, the coupling constant is 0 to 2 hertz, so you may or may not see it, okay? Same with around a double bond, you have coupling constants. And so if you've got a vicinal cis interaction, you've got about an 8 to 12 hertz coupling constant. Trans around a double bond, even though it looks like they're really far apart, they actually have the largest coupling constant, 12 to 18 hertz. Vicinal, so that means we've got a proton here, and then we got a carbon, and then a proton off of it. It's about 6 to 8 hertz. And allylic is proton here, then carbon, 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 and then proton, or carbon, 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 and then proton is about 0 to 3 hertz. So you may or may not see that really well. Okay. So I'm going to go through now an example of that. In your lab manual on 1614 is this compound, trans 2,4,5 trimethoxy prophenylbenzene. And so it's got all sorts of different coupling around that compound. So we've got the trans coupling, we've got the vicinal coupling, and then we've got, allylic coupling, and then the vicinal coupling to look at, okay? And so one of the things that you can draw when you've got these coupling constants, besides calculating coupling constants, in order to help you to calculate the coupling constants, you'll draw splitting trees. And so what you want to do is draw these, you can draw them as a prediction of what you'll see, and then look in the actual spectrum and draw this, what you actually do see in the spectrum, okay? So if we kind of try and get all our pieces up here, okay? So we've got our compounds here, okay, or the compound here. So first of all, if we look at our trans interaction, when you're drawing a splitting tree, you're always starting with the largest interaction at the top. So we've got HA is split by HB, so we've got one split here due to HB. And in a little bit in lecture, you'll cover what, if you haven't covered the N+1 rule, you'll cover it this week, okay? So if you have a proton that is splitting another proton, you split into N+1 the number of protons that is causing the splitting, okay? So HB is causing the splitting for HA. That's one proton. We've now split into two things, okay, N+1. Now, in that splitting, we then have splitting 0 to 3 hertz due to the CH3s for HA, okay? And so that is an allylic relationship. And because we've got 3 protons, we've got it split 3 times. So we've got 1, 2, 3. When we do that, we end up with 4 peaks here and 4 peaks here. So We have 3 plus 1, we get the 4, and then we've got a pair of those. That's from the initial trans splitting, okay? So we've got a doublet of quartets due to the trans splitting and then the allylic splitting. Over here, HA is splitting HB by 12 to 18 hertz. And then the relationship of the CH3 is it's a vicinal relationship, and so that's a greater coupling constant. And again, we've got 3 of those in the methyl group. So we've got split once, twice, 3 times. We get 4 peaks down here twice. So we get a doublet of quartets, but this time, because the splitting was so large, we actually get overlap of the 2 quartets. Okay? So there actually is 8 peaks down here from the 2 quartets. It's just right here, they're overlapping each other. And so this is what's predicted. Now if we look at the actual spectrum, this is HA, and so we've got this spectrum that looks like kind of, we can see doublets, and then we can kind of see the shoulders here that actually show the quartet. So we've got this doublet that then doesn't have completely defined quartet, but we've got a doublet of almost quartets, okay? And that was because the splitting from the CH3s was so small, you don't quite see that splitting completely. With HB, which was split by HA, we have a doublet of quartets, and you can actually see all of the peaks of the quartet. So we've got 8 peaks here, but it started out as a doublet, and then we've got our 4 peaks, or our 8 peaks down here, and we've got the overlap due to the overlap of the quartets, okay? And so the center of that doublet is right in the center of each of these peaks. So the center of that signal is right down the center. So the chemical shift for this doublet of quartets is right down the middle of that doublet of quartets, okay? So you calculate it right down the middle, all right? So this was a way to predict what happened. Then we look at what really happened and draw the splitting trees to show the reality. So in the end, our coupling constants were 16.2 and 1.4, and over here 16.2 and 6.7. Okay? Questions? Okay, so all of this is going to come into play in 16.